of the sample means. Sampling distribution of the sample means. And so when the samples get, let's just review that. So we'll go through these slides fast just to, remember we talked about the basketball. So the original variable was just height of the players. And then we took samples of size 2. And each of those samples of size 2 has a different mean. And then we look at the distribution of those means, right? We look at the distribution of those means. Okay? Here's the original variable. Here's the distribution of means of samples of size 2. And what did we say when you increase the sample size? What happens when you increase the sample size? The mean, so that with larger and larger samples, the means of those samples will more likely be close to the original mean. So what happens to the standard deviation of your sampling distribution for larger and larger samples? So does the standard deviation get smaller or bigger? Smaller, right? It gets smaller, which makes sense because with a larger sample, you expect the mean to be closer to the actual mean of the data. With samples of size 2, like you get two real low ones, or you get two real high ones, and then that mean will be far from the actual mean. But when you increase the sample size, now you're not going to have a cluster of outliers. You're going to get values from all over the population. So then the mean of each of those samples will be closer to the mean, and the standard deviation goes down. And that's, you can see it right there in the dot plots. And so then we put a number on this. We said to get that standard deviation, you take the population standard deviation and you divide by the square root of n. So the bigger that n is, the smaller that fraction will be, right? So for and that's just what we said, larger sample size means smaller standard deviation of the means. Okay, so then there's this thing called the sampling error. So here's where we picked up from last time. The sampling error is the result of using a sample to estimate, say, the population mean. So it's like when we use a sample mean to estimate the population, we're going to be off. It's not going to be exactly the same. And so if you take the difference, that's how far the sample mean is away from the population mean. And so that's the error. So this is how far off the sample mean is from the population mean. And really this should be absolute value. So the error is going to be a positive. So it's the positive version of that difference, okay? So if we took 3 basketball players' heights at random, and we got a mean of, let's just see here, go back. All right, so we take a sample, I forgot what the population mean was, 80. Okay, so take a sample of size 4. So here's one sample of size 4. And they got a mean of 78.5. So what was the sampling error for that sample mean? What was the sampling error for that sample mean? 1.5. And why did you say 1.5? Yeah, so how far are we from the actual population mean? That sample mean is 1.5 away. That's the error, right? So that's the error associated with this sample mean in predicting the population mean. So it makes sense that you would just take the difference of those two. You would take the difference of the population mean and your sample mean. That's how far away the sample mean is from the population mean, so that's the amount of error. Okay, and then we said that if you have a normal distribution, then the sampling distribution will be normally distributed. So this says that IQs have a mean of 100 with a standard deviation of 16. So with a sample size of 4, what will the standard deviation for the sampling distribution for samples of size 4 be? So what will that new standard deviation be? How do we get that? So standard deviation of the sampling distribution is, what do we do? Take the 16, right, and divide by square root of 4, right? Square root of n. It's your population standard deviation over the square root of the sample size. And so what is that? 8. So by taking samples of size 4 in this distribution, the new standard deviation becomes 8 instead of the 16 for the whole, for just the population distribution. And so remember what we said about just in general. One standard deviation is kind of where the curve is flat, right? So here's that one standard deviation, 8, just as a rule of thumb, right? A rule of thumb. One standard deviation is about where the curve is flat. And then what I didn't tell you, and maybe you saw it in the review video, 2 standard deviation is kind of this place where it's kind of the most curved, right? So it flattens out, and then there's this part where it's kind of curved the most. And that's about where 2 standard deviations is. So those are good rules of thumb to match up just the visual from a curve to where the standard deviations lie. So flat is plus or minus 1 standard deviation. And the most curved is plus or minus 2 standard deviations. So it's a good way just to kind of try to get your numbers in the right place relative to the curve that you're looking at. And that's true for any normal distribution. So this is what we talked about. With a larger sample size, you get a smaller standard deviation. So what does that mean? That means that your normal curve is going to be more squished and taller because more of the data is crunched around the mean when you have a smaller standard deviation. So here's the original population. That's the sampling distribution for samples of size 4 and then samples of size 16. And as this is just showing that same principle again, as sample size gets larger, your standard deviation gets smaller. Okay, what about when you have when you start with a population that's not normally distributed? So here, this is number of people in the household. Number of people in the household. Is that a left skewed or a right skewed distribution? Right skewed, right? Because in most households, it's looking like there's 1 to 3 people, but then there's a lower percentage of households with lots of people. So that pulls the mean to the right, right? So the median would be closer to 2 or 3. And then the median would be shifted over towards 3 or 4, okay? The mean, did I say median? So then the median's around 2 or 3. The mean is shifted to the right because of the households that have 6, 7, 8 people. But now what about the sampling distribution? Will it be skewed, right? So we've got a skewed distribution. If we start taking samples and make the distribution of the means, will that likewise be skewed like the original population is? So let's see what happens. So here's 3 different original distributions of populations. And then we look at larger and larger sample sizes, okay? So when you do samples of size 2, here's what happens. Of course, the normal distribution continues to be normal with a smaller standard deviation. We talked about that. But look what happened to the, so this is like, what, severely right skewed, right? Severely right skewed. What's happening when you look at the sampling distribution? See that it's not as right skewed? And then when you do a sampling distribution for a uniform distribution, you get more of the means are more in the middle. So what about if we up it to sample size of 10? What's happening to our sample distributions, I'm sorry, our distribution of means for a larger sample size? And so then here's 30. Not uniform. What is this called? This is uniform. So what is this distribution called? Normal, right? Normal. So what happens? Yes. When you keep increasing, as you keep increasing the sample size and you look at the distribution of means, that distribution of means becomes normal as the sample size gets larger and larger. And 30 is kind of the magic number. 30 is kind of the magic number for when you can consider any initial distribution to be predominantly a normal distribution. By the time you get to samples of size 30 and beyond, any distribution becomes normalized. And of course, with a small standard deviation. But now, if you start off with a normal distribution, you don't need 30. You see that? You don't need samples of size 30. If you start off with a normal distribution, all the sampling distributions will be normal. Okay? It's just when you start off with a non-normal distribution, it takes that large sample size of 30 or more for the sampling distribution to become normal. Okay, did that make sense? So if you start with a normal distribution of your population, any sample size will result in a distribution of means that's normal. When you start out with a population that's not normally distributed, this is severely right skewed, this is uniform, it takes about 30 or more in your sample size for your sampling distribution to become normal. And looks like even less for like a uniform distribution, looks like even 10 or 20 is pretty close to normal. Okay. And that's called the central limit theorem. Okay? So the central limit theorem, so don't write down every word, see if you can summarize, so we can move on. But for a relatively large sample size, the variable x bar, or the sample means, is approximately normally distributed, regardless of the distribution of the population. And the approximation to a normal becomes better as you increase the sample size. And so then here, roughly speaking, the farther the original variable is from being normal, the bigger a sample size you need for it to be normal. But in all cases, usually 30 is enough. That's what we talked about. So that's just a review of what we said. So that principle is called the central limit theorem. That with large enough samples, all distributions of means with a large enough sample are normally distributed. So here's that household size. There's the original population, right skewed, and this is now for samples of size 30. Here's the distribution of samples of means for samples of size 30, normally distributed. Okay, this is just a summary. This is a summary of everything we've talked about. Okay, so variable x, population mean mu, standard deviation sigma. For samples of size n, we said the mean of all the samples is the population mean. So this is our first important fact. That if we took the mean of the means, that's what this is, the mean of all the means is going to be the same as the population mean. And then we said the standard deviation of the means gets smaller for larger samples, and you calculate it by the population standard deviation divided by square root of n. And then here's what we just talked about. If x is normally distributed, then so is the distribution of means, regardless of how big the sample is. Okay? If the sample size is large, then the distribution of sample means is normally distributed no matter what the original population distribution was. Okay? And the kind of 30 is the magic number. So that's a summary of everything we've talked about there. Okay, so let's just do one quick. Did we do this example on Monday? The New York City? I don't think we did. We didn't get this far. Okay, so this is the finishing times for people in the New York City 10K. The mean was 69 minutes. That's the population mean. Sorry, 61 minutes. Average finish time for the 10K was 61 minutes. And the standard deviation was 9 minutes. That means, and so what does this mean? That means that, just to review, about 95% of finishers finished in what range of times? Figure that out. We should remember this. This is really important. So everyone should get this. Review. Should be able to do it without a calculator. Okay, once you get that review question done, then we'll do this. We'll do everything except C. We'll construct a graph. It gets to the end, we pass it to the graph. That's what I do. Okay, so let's our review question. How did we do? I know Heather got it. Let's see, Daisy. How did you do? Did you get this review question? No, do you remember what 95%? How do we know the 95% range? Remember what that is? Do you remember? What is it?
It's 2 standard deviations.
Okay.
I did 61 plus 18 and 61 minus.
Right. So if you go up 2 standard deviations and down 2 standard deviations, you have your range where about 95% of the data lies. So what'd you get? 43 and 79 minutes. Okay. Okay, so whenever it asks for a sampling distribution, it's asking for 2 things. What is it asking for?
do you want to do the sample size model? Are we still doing this? Okay, 56. So minus 167 is 0, 1, 2, 3, 4, 5, 6, 7, 8, 4, 7, 5.
So I'm guessing in the low 70s%. What'd you get? 73 point. Everyone able to get that?
Yeah, I got it.
Good. 73.3% of sample means will be between 56 and 66 minutes. If you use just size of 4, sample size of 4. Make sure you're able to get that number. If you're not, get help. If you
So it says for percentage, when it's asking for a percentage, it's always going to be the z-score?
not the z-score.
I mean,
The z-score helps you get it.
Z-score helps you. I mean, in other words, you have to use the formula for z-score in order to find the percentage.
Remember we said area under the curve correlates or is equivalent to percentage of the data. Area under the curve is percentage of the data, and your z-scores, then using your chart, get you those areas.
And the sample size was 60. 61.
Yeah.
So I'm pretty sure I got the right answer for E.
Okay.
I know I got it for E, but I'm still kind of confused when it says interpret your answer.
Okay. Okay. Yeah, we're gonna talk about that.
responds positively regardless of the distribution.
So,
Confusing, to say the least.
all right, so let's talk about, so what does sampling error have to do with this? So we've got 73% of the samples of size 4 lie between 56 and 66. What does sampling error have to do with that? So where does sampling error come into that picture of things? What sampling error are we talking about?
It's just like the difference between the sample that we use and the population.
Okay, so what in this particular case then what sampling error are we talking about?
Would it be the error of the area under the?
Nope. So no, error just has to do with how much error there is from the sample mean to the population mean. So what amount of sampling error are we talking about in this case? Right? So it's how far your sample mean is from the population mean. What's that? Yeah, so the error we're talking about here is plus or minus 5 minutes. 5 minutes from the mean, right? So 73% of all sample means have a sampling error, what?
Plus or minus 5 minutes?
Equal to 5 minutes?
Plus or minus 5 minutes.
Not equal to 5 minutes. A sampling error equal to 5 minutes would be 66 or 56. What does the 73% refer to? No, it's all sample means between those, right? This was all sample means that are from 56 to 66. That's why the area is shaded here. So 73%, 0.3% of sample means have a sampling error what? Of sample means. What can we conclude? 73% of sample means, those are the ones that all fall in here. What about the error of all the ones that fall in the shaded region?
Would it be 73% of 5 minutes?
What's the error if a sample mean was 62? What's the error? If you get a sample mean of 62, what is the error? How many minutes error? 1 minute error. Is that lie in this region? Okay, what about 58? If you get a sample mean of 58, how much error do you have? 3. Does that lie in this? What if you had a mean of 70? What would the sample error be for a mean of 70? 9. Would that lie in this? No. So 73% of all sample means have a sampling error, what? 5 minutes or less. 5 minutes or less, right? Because the error is your distance away from the population mean. How much error, how far you are away. So means like 57, 58, 59, 60, 61, 62, those are all have a sampling error less than 5. Right? Because they're less than 5 away from the population mean.
So it's only less than 5, it's not less than or equal to 5?
Oh, yeah.
Maybe plus or minus 5?
But the sampling error is a positive number. It's not negative. So you wouldn't say negative. Your error is negative down here. It's still positive. So you're just distance away. Just distance away from the population mean is the error. So if you had 57 minutes, that error is 4. Okay, if you have a 57-minute for mean, that error is 4, and that is part of the 73% of all sample means, right? Because it falls between 56 and 66. Yeah, so less than or equal to, I'm actually, does that make sense? The sampling error makes sense. Okay, can we go on? Let's press on. Our last chance for one more question. Okay, here we go. So let's do this one. Price of history books. Go, you can do it. All by yourself.
On the blue paper?
Yes, on the blue paper. And if you ever want to put these in your notes, you also can put them in your notes.
Yeah. Yeah, you do the 84. I 81.44 minus the 70 divided by that. So you have this plus 2. Yeah. And that would be fine. This is 40. And we can get the percentage so that.
Oh, it changed the implementation. It changed yours in the scientific notation. That's the right answer, but it's that
It's on the back side.
That's the percent.
And then the homework's due Sunday, right?
Sunday night.
It'll be like
And they'll be written too. They'll be written work too
Okay.
on Blackboard.
and then the percent would be 62%.
So the assumption is that
yeah. So that's gonna be less than 1%.
So I did this, and I got 0.8. Right? So then I can use this for, and then I can use it for right? Or do I do one minus this? One from the area, not from
Okay, so when you get started on these problems, here's how you have to have it structured in your brain. Okay, you have a population distribution. The distribution consists of a mean and a standard deviation, and that was given, right? So this is the population or the mean and standard deviation of retail prices of history books. Then we take samples of size 40. Those means of those samples of size 40 have their own distribution. They have another distribution that comes from the population distribution. So what is the mean of those samples? The mean of the means, right? So this is the mean of the means of samples of size 40. What is it? No, but it's the mean of the means, right? So we're going to take samples of size 40 and we're going to get a mean for each sample of size 40. What's the mean of those means? That's what this is. What will the mean of those means be? It'll be the same as the population mean. It'll be the same as the population mean. We saw that, right? Like with the basketball players, right? And then, what will the standard deviation of those means be? Will it be the same as the population standard deviation? Will it be bigger or smaller? It'll be smaller. We take means of size 40, or samples of size 40, then those means are going to be a lot more tightly bunched around the mean. So what is it? It's 7.61 over. So you have to, when you're doing these problems, you have to have in your brain that there's two distributions. There's the population distribution, characterized by a mean and a standard deviation. And then there's a distribution of sample means. That distribution of sample means will have the same mean. The mean of the means will be the same as the population mean. The standard deviation of the means will be the smaller number. Will be smaller because of large. You have a sample size bigger than 1. So when you're going through problems like this, that's what has to be happening. And write it down if you need to. There are two distributions. There's the population distribution, and then there's the distribution of sample means. And then now they're asking for what percentage of samples of size 40 have a mean greater than 81.44. So are they referring to the population distribution or the distribution of means when they're talking about this 81.44? Which distribution are they talking about? They're saying they want samples of size 40 that have a mean greater than 81.44. So is that going to be the population distribution or the distribution of means? Distribution of the means, because this is a mean of a sample of size 40. So you're going to compare that in the distribution of means. Is it better? Does it help? So this is kind of how you have to see these problems. There's two distributions that work, the population distribution and then the distribution of the means of the samples. This number refers to the second, right? Because it's talking about, this is a mean retail price of 40 books. So you're gonna use this down here when you do the chart and stuff. Okay, there's one more thing we have to do so you can be ready for the homework. So we good on this problem? Any more questions? Okay. So a point estimate, so here we go. Parameters are values associated with a population. Statistics are values associated with a sample, and it's really easy to remember. Look, P and P, S and S. Okay, so you got a nice mnemonic device there. Parameters are values associated with a population. Statistics are values associated with a sample. So a point estimate is a statistic used to estimate a parameter. A point estimate is a statistic used to estimate a parameter. We've already done that. How have we already done that? How did we use a statistic to estimate a parameter? Or what's an easy example of that?
Is that the z-score the area thing?
Nope, even easier than that. So a statistic would just be like a sample mean, right? So your statistic would be like taking the mean of a sample. And what would that be a point estimate of? What would that be a point estimate? What would that tell us about the population? What could we estimate about the population by taking the sample mean?
Average,
The average of what?
the sample.
We already have, that is the average. So the statistic, so the sample mean is a statistic, right? Sample mean, X bar. What is that a point estimate of?
The middle of that sample?
No, it's not an estimate. It's not an estimate of anything to do with the sample. It is the mean of the sample. It is the mean of the sample. So we're now, what can we estimate about the population given a sample mean? It's so easy.
The average, the mean or the average of the population.
Right, the population mean, right? So it's an estimate of, so it's like, what's the average age of students on campus? Well, we take a sample of 50 students and we get the mean of those 50 students. And then we say, oh, this is an estimate for the population, all students, the average of all students' ages, right? So sample mean is a point estimate of the population mean, mu. It should make perfect sense, right? We can't average all ages of all students, but we can take a sample and get the average of the sample, and then we say, this is what we estimate the average age of all students to be based on our sample. That's all it is. Make sense? That should be a very easy idea.